How to do nucleophilic aromatic substitution. Okay. The first point that we need to take note of is the fact that in nucleophilic aromatic substitution, our aromatic ring is the electrophile that is going to be attacked by some nucleophile. And this nucleophile is going to attack at some site where there is a leaving group. There's going to be an electron rearrangement within the structure. And this is going to allow a replacement of the leaving group with the nucleophile. So, in this case, we have to think of, is a nucleophile going to attack our chlorine or fluorine? Because both are potential leaving groups. Well, let's consider it replacing the fluorine. Imagine it were to replace the fluorine. If this were the case, the electrons on the methoxy attacking the fluorine site would cause this double bonded electron pair to move positions because we can't have hypervalency. So if that moves to this position, that would mean that this must move to this position here. The problem is that the methyl group is an electron donating group, meaning it donates electron density into the ring. And we don't want, since it's donating electron density into the ring, it doesn't draw the density onto itself. It's not going to take electrons. We want an electron withdrawing group to do that. Something that is sucking electron density towards it, a substituent that wants the electrons. So we know that methyl is an electron donating group. However, our NO2 is an electron withdrawing group. Consider the resonance structure. You could see that there is a potential for this NO2 to appear in this conformation by means of resonance. And so it's also another way you can kind of tell that it's an electron withdrawing group is that there isn't a lone pair directly attached to the carbon. In general, electron donating groups would include things such as your hydroxyl, halogens, and H2 and alkoxy which is like an oxygen with an R group, and an alkyl, such as methyl. Contrary, an electron withdrawing group, the three big examples are NO2, a carbonyl, which would be some R group attached to an R prime group, double bonded to an oxygen, and also cyanide. So now let's consider attacking at the chlorine. If we were to attack at the chlorine, this electron pair would move to this position, and this double bonded pair would move to this vicinity, where it could be either a carbanion or attack to make this resonance structure. Note that if we tried to make this, if we tried to attack at the fluorine and move the electrons in such a way that rather than having this electron pair move to the carbon, we had it move to form a double bond here, and we tried to move this double bond down here, that would cause this carbon to be hypervalent, so we can't do that. Therefore, attacking at the chlorine is our option. So now, let's consider the drawing it out with the resonance structure of NO2, as we already described before. So this is what the structure looks like when you have the withdrawing group drawn out, and it's easier to see that electrons can there could be a resonance structure that causes the electron density to draw onto the nitrogen species. And so we're going to consider the two scenarios we mentioned earlier, the carbanion and the resonance structure. So for the carbanion structure, the methyl group is going to come and attack the chlorine. Now, this lone pair is going to come to this side, switching positions. This double bonded pair of electrons is now going to slide onto the carbon. Notice there's no hypervalency, so we're all good. Now, if we were to withdraw the resulting structure from this, it's a little sloppy, but it'll show. So, the methoxy attacks the chlorine position to carbon. So we're going to have the chlorine and the methoxy on this one carbon. This double bonded pair moved over to this position, and this double bonded pair formed a lone pair on this carbon. And you can note the central carbon here has 1, 2, 3 bonds, and then the 2 electrons for a total of 8 electrons. Therefore, it's not hypervalent. We're all good. Now, of course, we're not done, because the whole point of a nucleophilic aromatic substitution is to substitute our nucleophile with the leaving group. Now, to do that, we're going to move back the electrons in the same fashion. This lone pair is going to move back to its original spot, and this double bonded pair is going to move back to its original spot. Now, the chlorine, the electrons attached to the chlorine, are going to leave with the chlorine. And this is going to result in a structure as seen here. With the methoxy taking the place of the carbon, and of the chlorine, methoxy taking the place of the chlorine, and the chlorine forming an ion. Okay, so that is going through the mechanism where we end up with a lone pair forming on this carbon, forming a carbanion. And that is the Mesenheimer conformation. Separate this. Now, our other possibility is for our electron withdrawing group to suck on that electron density, and rather than form a carbanion, we form somewhat of a more stable conformation. Although both are completely viable options. So in this case, our methoxy again attacks the chlorine at that carbon. This electron pair would move again here. And this double bonded pair, the difference now is that it's going to move to form a double bond with the nitrogen. However, that would cause hypervalency. So, as this double bond forms, this double bond breaks, allowing the electron pair to move on to the oxygen. This would result in structure such as this. And the oxygen would have picked up a negative charge. Okay. Now, in a similar fashion to before, we're just going to move the electrons back in the way they came. So, this electron pair would reestablish a double bond between the oxygen and nitrogen. This double bond would break, moving back to this original position. This double bond would move back to its original position, and this chlorine would leave. As a result, we would get the same outcome. So notice that there is two different mechanisms that go through a similar yet slightly different process. Well, the same process, but go through slightly different intermediates. But in the end, we can come out with the same solution. Same products. And so this is your more preferred mechanism, just because the electron withdrawing group taking on that electron density is more stable and energetically favorable. However, this is completely a viable option as well. And that is nucleophilic aromatic substitution.